Hello everyone. In this video, I'm going to be going over the MacNCheese serial plotter, what it is, and how to add it to your project. So starting off with what it is, it's a logic analyzer that when added to your project will display to you in real time what up to 8 signals are doing within the system. It's similar to an oscilloscope, but after it's added to your project, it's much easier to use and see what exactly signals are doing. So I have the project opened up in Radiant right now of just the serial plotter. So this is the highest level entity of it and the one you will be adding to your system. So I will be going over the different options and ports within it to start so you understand how it works. And then after this, I will give a live demo of adding this to an example project. So looking at the generic values first, the first prompt is whether or not we want to use the RAM on the chip. For most applications, I would say not to use the RAM, so leave this at 0 because that will let you read it in real time. If you are reading faster than 20,000 samples a second, or you want to read something immediately once the FPGA starts up, then you would want to use the RAM, in which case you put this to 1, and the data will be sent into a buffer, and once that buffer is full or prematurely quit, it'll send that data to the computer with the trade-off of not being able to see it in real time. And the next two options here will let you tell the system how fast you want to read the data. So the simpler method is if you want to use an external clock, you have a clock on your system, you want to read data every time there's a rising edge of that clock, you set that to 1 and you map that clock you want to sample at to this external clock port here. If you do not want to use an external clock, you have a set byte rate in mind you want to use, then you simply just set this to 0 and you can safely ignore this port on your mapping. And from there, you will then edit this byte rate value. This tells you how many samples you want to read at a time, as there are 8 bits in a sample. Each sample is 1 byte of data. So it's currently set to 100 bytes or samples sent to the computer every second. So you could edit this however you please. Just keep in mind not to keep it too high, as there's a limit to how fast the FPGA could send data to your computer. The next generic term, you could ignore. That num inputs is always going to be 8. Please do not change that. And the last two are regarding the RAM, and it tells you how many samples you want to store at a maximum. You could always prematurely quit within the software, but if you're reading super fast and only want to store a certain amount, you could edit these to larger values. Keep in mind the FPGA could only store 1 million bits on its system, so not too many samples that can be stored. And whenever you do edit this num samples, you will likely have to edit this address with value 2. It is the log 2 value of however many num samples. So if we were to multiply this by 2 to 2048, then address width would have to be 11. And looking at the port map, this data in, it's a standard logic vector of 8 bits, and these are the bits you're going to probe and the bits that are sent to the computer. So keep in mind that you do have to port map a whole byte to the standard logic vector. If you only want to read 1 or 2 signals, you could just have those 2 signals as the first 2 bytes and just zeros for the rest, or don't cares. So this is basically the data that you want to read. The next one is a clock 48. It's a 48 megahertz clock that needs to be input into the system, simply because there's only one high-speed oscillator on the chip, so we cannot have this in both your design and this plotter. And we went over this one. And these 3 values simply need to be output through your top file and mapped to these 3 pins here. This is to help make the serial communication through USB work with the FPGA. So make sure they're port mapped appropriately and sent through the top level module. So now that we understand how the MacNCheese component works, let's go through the process of adding it to a project. And the project we will be adding it to is this simple counter project I have. And to add it, there's two main methods. The first of which being a script that we wrote to automate the process for you, and the second being to do it manually. I'd recommend the script as it's a whole lot easier. And to do so, you first need to make sure that you have your project saved in your Z directory. If it is not in that directory, then you will run into problems later on, most likely. And you also won't be able to use the script. So I would highly recommend moving your project into the Z directory if it's not there already. So once our project's there, the first step is to log into the Halligan servers over Secure Shell or a Linux machine.
So for those who don't know, this is the command to log into Halligan servers remotely from either Mac or Linux. Keep in mind, this is my personal username and yours will be different, so make sure to write your own personal username when entering this. And now that we're logged on, we want to change directory into that of our Radiant project. And as I called mine example, and it's in the home directory, this is how I would do it. Should be a little different for yours, just based on where you stored it and what it's called. And once you're there, just to double check, this is what your directory should look like. And now all we have to do is download and run the script within this directory. To do so, we could type in this command with this URL to download it from the internet. There should be a link in the description, as it is kind of a long link to type in. But once you hit enter, it should download pretty quickly. And in order to run it, all you gotta do is type in Python 3 setup.py, run it, and if there are no errors, this is what the output will look like, and there you go. That's pretty much all the work to add it to your program. Now, I would highly recommend running this while Radiant is closed, and then opening up Radiant, or at the very least closing Radiant after running this, and then opening it back up. So I will open up Radiant now and show you what it looks like.
So looking back at Radiant, we can see that there were a bunch of new files added to the project. You don't have to do anything with them at all, just make sure that they were all added. And then the only other thing the script does is mess with the top file. And we can see here that it adds these three IO values. And these are used to send data to and from your computer through the serial connection. And the script tries to edit the device constraint editor here, but it doesn't always work. So double check that these three values are correlated with the three signals here in the device constraint editor before flashing. The next thing it does is it adds the MacNCheese component within your top file. And then it creates a framework for a port map right here. And these generic settings we talked about before, currently it's set to a continuous read without using the external clock at 10 bytes a second. Feel free to edit those however you want, but for now we'll keep it as is with the default values. And for data in, this is the 8-bit logic vector we want to probe. I already had it pre-written out right here. So I would like to probe my test data logic vector. Clock 48 is a 48 megahertz clock. It should be the one in your high-speed oscillator port map. I need mine clock 48. And external clock, if you are using an external clock, make sure to port map be here. But as I personally am not, I shall delete this line as it's not needed. And now I save it, I get 0 errors, and I'm good to go. That's the extent of the process running the script to add the MacNCheese sampler to the project. All that needs to be done is flash it and open up the GUI section on your own personal computer while it's running.
For the manual edition, it's a bit more involved, and what I have pulled up here is the GitHub of the MacNCheese repository and the VHDL files within it. And what needs to be done is each of these VHD files needs to be downloaded and added to your Radiant project. I will skip that section of the recording as it's long and tedious, but make sure you do this, and from there I will hop on Radiant and show you the next steps.
First thing we want to do is make sure that we have all the required input files added to our project on this end. So double check that real quick. And once that's done, we'll go into this MNC file and grab the entity and add it as a component within our system. Easiest way to do that is copy paste the entity and change entity to component, like so. And now that that's done, we can safely get on with the port mapping of the system. So I'll add it under the oscillator port map right here. Simple template just to ease the process. So first value to consider is, do we or do we not want to use the RAM? As for the example, I will just be probing the first 8 bits of this counter value. I would assume that's going slow enough to where I do not want to use the RAM. So I'm going to set this to 0. And then as far as how fast I want to probe, I'd like to see this in real time. And as such, I also do not have a clock within my system that I am in need of using. So I'm going to say no. And to keep it smooth, I'll say I want a byte rate of 100. And this will give me 100 samples every second of the 8 bits that I'm probing. So from there, going on to the port map section. Data in, this needs to connect to an 8-bit standard logic vector, as that is what data in is. So I will create a signal in order to do that, as I currently do not have a 8-bit standard logic vector within my system. So signal test data is standard logic vector down to, make sure that's 7 down to 0. And it is worth noting that you are able to probe just 1 or 2 values, or any number up to 8 if that's all you want. You just have to make sure that this test data signal, or whichever one you're using, has the first 2, 3, however many bits you want, filled with the signals that you want to probe, and the rest of them could just be zeros or don't cares, and you could ignore them when you're reading it on your computer. So now that that signal is declared, we would want to wire that up to the counter bits that we want to actually read from. So we take our test data and we set that equal to counter 29 down to 22, as that is the top 8 bits. However, that's also an unsigned value, so we need to do a type change into a standard logic vector, like so. So now our test data is holding the counter bits we want, and now it's an established signal. So now we could take our data in and map it to test data, like so. Next up, clock 48, as we have our high-speed oscillator here. Pretty simple port map, just straight to clock 48, or whatever name you have for your 48 megahertz clock. And now for the input-output pins, on the UART as it's called. We currently do not have them in our top because we're not using any UART here. So if we go into our MacNCheese, we could take these 3 signals or IO values from here and just add them to our top entity like so. And then we go into our port map and we could just map them as is. Pretty straightforward. The one other thing you do have to do with these is make sure they're mapped to the right pins. So serial RxD always has to be 15, serial TXD always has to be 14, and SPI CS always has to be 16. You're not going to see those pins on the sides of your FPGA. Those are internal on the actual board and are used to connect the output data to the USB port. So that's all you have to do if you want to probe it, if you want to add the MacNCheese to the system. Then you just got to synthesize your design and then flash it to your FPGA and you're good to go. But let's say I did that and I want to play around with some other settings with this MacNCheese plotter. So let's say for starters, I did want to use RAM. Well, first thing, we got to set this to 1. And now if we are using RAM, we're currently taking 1024 samples. If that's what you want, then you can just leave this as is. You don't need to redeclare them. But let's say I want to use 24 day. I need twice the amount of samples. So then I would just paste this, and then I would set it equal to 2048. And because that's changed, I now need to change the address width value. I need to change that to log 2 of 2048, which is 11. So this is how I would then save this, flash it to the synthesize and then flash to the FPGA. And that's how I would use the RAM. And now let's say I no longer wish to read a data at 100 bytes. I want to read only when this test data changes. So I could do that by having the use external clock value set to high. But in addition to that, I would also need to actually port map this external clock in. So I will create a signal right here, signal external clock, and standard logic is the type for this value. And in order to have, as this is a counter, in order to get these 8 bits incrementing once per read, this external clock value should be mapped to counter 21, because what's happening is every time there's a rising edge of counter, then the sampler or the MacNCheese will output test data to the computer. So every time there's a rising edge of external clock, then there's a new counter 22, right? Because counter 22 goes high, low, and if you're probing every single high of counter 22, you're missing every other bit change. So for this case, we want to use counter 21. So now we have that. We have to say external clock is external clock. And in this situation, we are now probing using RAM and with the external clock, which is declared here, and probing every time that this counter value changes. And that's all I have for the VHDL portion of the MacNCheese logic analyzer. For the software side, there's some links in the description to the GitHub where some easy to download links for the software are available. And from there, running it and viewing your logic should be pretty simple and straightforward. Now, if you do have any issues running this or encounter any bugs, please reach out to a TA or professor so that we could get that fixed in the future. And so now hopefully you're all set to actually add this to your design. So have fun with that. And we hope that this system will help you and your peers debug your VHDL designs.